Section 4 of the Lines and Triangles unit is going to look at some more of those special lines and segments and relationships that exist in triangles. The first one is a special theorem called the exterior angle theorem, and it applies to triangles. So just in review, we all remember that the sum of the interior angles of a triangle equal 180. Well, we don't always know all of the equal or the inside angles, and sometimes we're interested in those exterior angles, and it's nice to have shortcuts sometimes. So what the interior angle theorem says is that the sum of the two remote interior angles is equal to the exterior angle. Now what that really means is the two far away inside angles added together equal the one exterior angle. And so we can set up an equation and solve for any part of it being missing. Now don't forget that these two angles right here form a linear pair, and so the two of them together equal 180, and so there are a multitude of ways to solve for missing angles in and around triangles. So if we look at an example to apply this theorem, in this situation we have an x and a y. So the first thing I'm going to do is use that linear pair theorem and find y. And so I know that y plus 92 equals 180, and that is by linear pair theorem. Use my algebra skills and subtract 92, and I end up with y being 88. Once I know that y is 88, I could go ahead and I could either use 50 plus 88 plus x to solve for x, or just to test our theory, I could take 50 plus x, and that would also equal 92. Either way you do it is correct, and that's the beauty of geometry, is often there's more than one way to get the right answer. So if I subtract x from both sides, or 50 from both sides, I get that x is 42. Now by doing it that way, I left myself the opportunity to check, and my check is that the sum of the interior angles, 50 plus 88 plus that 42 I just found, does that equal 180? And so either using the exterior angle theorem or the triangle sum theorem property, I can check my answer if I've used a different method. And this indeed does work, so I know I did my problem correct. In this situation, the triangle sum doesn't help me directly. I could use it, but it'd be some convoluted algebra involved. So why not work smarter, not harder, add these two together, and they equal this outside angle. So 25 plus x plus 15 is going to equal 3x minus 10. So a little bit of algebra, combine like terms first. 40 plus x equals 3x minus 10. I don't want to deal with a negative on my x, so I'm going to subtract x from both sides. I'm going to add 10 to both sides, divide by 2, and x is 25. Again, you can put it in and check and make sure everything is correct. Another very important theorem that we have that is used in a lot of different forms for proofs is the perpendicular bisector theorem. Now in the last section we defined a perpendicular bisector, and we said it could even take some crazy forms like this, because we said by definition it had to be perpendicular and bisect. Okay, so this is the definition of perpendicular bisector from section 3. Where we become interested with the perpendicular bisector is if a point is on the perpendicular bisector. A point on the perpendicular bisector, like D, H, and F. This is when things become interesting. So remember in our conditionals, P implies Q, This part we hold true, and we look and see what happens to the then. Here's what happens for the perpendicular bisector. 2 points. It is equidistant from the endpoints of the segment, and it bisects the angle. So by definition, that is true. It is perpendicular, and GF and EF are equal. So by definition of perpendicular bisector, I know that GF is equal to FE, and I know that that angle at, let's call it DFE, is 90. Now additionally, what I get from the perpendicular bisector theorem, I additionally now know, because this point D is on that perpendicular bisector, and this information right here tells me that. Since D is on, I know, let's make this a different color. I know that it is equidistant to the end points. So I know that DG is equal to DE. I know that HG would be equal to HE. And I know that these green ones down here would also be equal, that GJ would be equal to EJ. That's the equidistance from the endpoints. Now we've talked all along that the direction of the bisector matters, and by definition it's bisecting this way. But once that point is on the perpendicular bisector, it actually bisects both ways. So we get that all of these angles also become equal. And so we could list all of those angles in order. I'll just do a couple. That angle GDF would be equal to angle EDF. And if we could go down to H in the red, that angle GHF is equal to angle EHF. And the upside down one, angle GJF, would be equal to angle EJF. So between the definition and the theorem, we get a significant number of pieces of information for that whole concept. If you know a point on with a perpendicular bisector, you get all of the definition pieces, equal segments, right angle, and all of the theorem pieces, which are equal segments and equal angles. Go ahead and tune into the next video where we're going to talk about coordinate geometry.